The energy harvester uses levered multilayer piezoelectric biomorphs, otherwise known as an LMP, to maximize energy generation. This system centers around a piezoelectric pad which translates the kinetic energy of walking into electrical energy by utilizing piezoelectric biomorphs. This is possible since piezoelectric crystals output an electrical charge when under mechanical stress. In order to maximize the power output of this system, various methods were implemented. To increase the displacement of the pad and thus increase power output, the LMPs are clamped to a pivot on one side while the other is pined, which disallows movement in the vertical direction. When the footstep force is applied on the short lever arm, the piezoelectric patches on the long arm will produce increased electrical charge due to the amplified displacement and thus amplified mechanical stress. A spring will also be used to return the piezoelectric pad to its original position. So though a portion of the input force is required to overcome the spring force, the spring will facilitate a continuous vibration by providing a return force. A majority of the structure is 3D printed using PLA, and the piezoelectric biomorph consists of a brass substrate layer with two piezoelectric patches on each side connected in parallel. The Adidas MyCoach Speed Cell Footpod was chosen for its low power draw and, using Bluetooth Smart, its ability to communicate data such as speed, distance, and stride rate to an app in real time. The use of this sensor will also be somewhat of a proof of concept, displaying this energy harvester's capabilities to power portable biometric sensors without a need to replace batteries. The battery fills almost 40% of the space of the sensor as well, and thus energy harvesters can drastically reduce the size of portable biometric sensors by removing the need for one. Power generated by the piezoelectric pad is collected as AC current, and a high-efficiency AC to DC interface circuit, a synchronized switch energy harvesting on inductance, SSHI, was developed to generate DC power. A DC to DC converter was then used to obtain a stable voltage at 3.3 volts. With a supercapacitor, the converter can replace the battery originally used in the sensor and allow for a more compact design by dramatically saving space in the sensor. To integrate the system, the heel of the boot was cut out, allowing a protective enclosure containing the energy harvester and circuit to be sheltered within the boot. This will guard the system from the elements, and the box will be covered in a protective layer that also provides grip on the bottom. The unintrusive design allows for an undisturbed walking gait, providing the opportunity to generate energy without hindering normal locomotion. This is displayed by a user walking, and it can be seen that the device is almost undetected until careful consideration. After the user walks for a while, the sensor becomes powered and begins communicating the appropriate information to the app, as can be seen. The success of the energy harvester is displayed as the sensor receives enough energy to perform as intended, measuring the speed, distance, and stride rate of the user.